Thanks for the introduction, Omnia, and for inviting me. It's a great pleasure. So in this next lesson, I actually want to talk about a series of projects that I did 2 years ago when both you and I were defending our PhDs. And we thought that this could be a topic that is also interesting to the students in this class. It's about adapting encoder models to low resource languages. And specifically in these projects, we worked with low resource languages from Switzerland, but I hope that the methods that we used are also applicable to other language situations in other countries. Yeah, so as you might be aware, Switzerland is a multilingual country, so you might recognize some languages that are spoken in Switzerland, such as German or what else? Italian, French. So these are 3 national languages that are officially supported by the federal government. English is also a language that you can talk to most people in Switzerland, but it's not an official language. Now, you might also recognize languages in the other speech bubbles. So what I see here is Albanian and Romansh. So Romansh is a language that many people actually do not know. It's the 4th national language of Switzerland. So it's also officially supported by the federal government, but it's a minority language with few speakers. It's a Romance language, so it's from the same language family as Italian and French. And Grüezi is actually a dialect. It's a dialectal form of Swiss German that people speak in Switzerland. So 5 million of the Swiss population in spoken communication, they use Swiss German. So geographically, it looks a bit like this. As you can see that the languages are not equally distributed. The majority language clearly is German or Swiss German when spoken, and Romansh is a minority language, maybe even an endangered language with a small speaker population. So in this language situation, our research question 2 years ago was, can we create an encoder language model that can understand written text in all 4 national languages of Switzerland? So German, French, Italian, and Romansh. Now, at this point, maybe I should refresh what I mean by an encoder language model, because it's not the same as a large language model like ChatGPT. It's a different type of language model. And specifically, generative models like GPT or Llama, obviously you can prompt them with natural language text, and what they output is also natural language text. So it's text to text. With encoder models, it's a bit more technical. So the input is text, but the output is a vector. It's a high-dimensional vector representation of the text. In the public sphere, when people think about NLP or linguistics, they think about generative models because generative models are useful for end users. End users can use them as assistants, as chatbots, and directly instruct them using natural language and get something back that they can use. Encoder models, on the other hand, are more interesting in a professional or technical context, because you need to be able, as a user, to deal with those vectors and do something with the vectors. Having said that, encoder models are still relevant, even in the era of LLMs. And I can explain to you why. But I saw that someone raised a hand, or? No?
No, it's okay now.
So why are encoder models still relevant in the era of LLMs? So first of all, they are efficient. The largest Llama model of the Llama 3 family, released last year, has 400 billion parameters. BERT model, which is an example for an encoder model, has 400 million parameters. So it's the same architecture, but it's 1,000 times smaller. And this means that it uses less energy, can fit on edge devices. For many applications, using an encoder model is the only reasonable option. For example, if you have a large corpus of text and you want to automatically annotate the text, or you want to search a large data set for something. In that case, it wouldn't be feasible to use an LLM for that task. So next, I want to cover the foundations of encoder models. So first of all, how are they trained and what can we use them for specifically? Omiya told me that you are familiar with the transformer architecture, more or less. And are you familiar with the idea of masked language modeling? No?
No.
So in the case of generative language model, everyone has an intuition how it can be trained. It's learning to predict the next word given the previous words, right? And on a technical level, this means minimizing the cross-entropy loss of the actually observed word in the training data with respect and like the probability distribution predicted by the model. So this is what happens when training a left to right or generative language model. With an encoder model, it's really similar. It's also about minimizing cross-entropy, but this variant is called masked language modeling, and it has first been used for the BERT model in 2019. So here we're not generating text from left to right, but the model can look at the complete text, except for a few words that are randomly masked. So they are replaced with a special token mask, and the model cannot look at the actual word that is here. So the model needs to learn to use the context around the word to predict what is the word that has been masked. So the transformer model will encode every token using self-attention. It will have a last layer containing the final hidden states. And these hidden states, there's one for every token in the input. These are taken as output embeddings that represent the identity of the tokens in context. So ideally, after it has been trained, the encoder model will predict an output embedding for this that represents the identity and linguistic properties of this here, and for tasty here. And then for the word that has been masked, the transformer will predict an embedding that represents the most likely word that was here. So we can use this embedding to then reconstruct the masked token, and this is what is used as the loss when pre-training the encoder. So by, technically by calculating the dot product between the predicted output embedding and all the embeddings in the embedding matrix for the complete vocabulary, we can calculate a probability distribution, and ideally the tokens that are most plausible here, they should have a high probability under the model. So chocolate and cheese, they should have a high probability because these are objects that can be tasty, and watch should have a low probability because it cannot be tasty. Let's talk about classification as one of the tasks that we can use encoders for. Classification can mean classifying individual tokens or words. So let's say we have a sentence like she lives in Geneva, and we want to look at every token and determine is it a city or not. This is useful for extracting city names from a data set. In that case, the encoder will predict an embedding for every token, and then we use this embedding as features for a classifier. And the classifier then, based on the embedding, will say this is a city or it's not a city. Classification can also happen not for individual tokens, but for a complete sentence or text document. In that case, a typical approach would be to average all the token embeddings into a single embedding representing the sentence or document. And then again, we use this sentence level or document level embedding as a feature for a classifier. Yeah, so many classical supervised NLP tasks can be phrased as classification, but my favorite tasks is actually text comparison. So here we have two sentences like the plant needs water and this flower is thirsty, and we want to estimate how similar semantically are these two sentences. And we can also use encoder model for this task. We will again let them predict an embedding for every token in the two sentences, and then we can compare the embeddings, for example, using cosine similarity between the embeddings. One approach would be to first average the embeddings for sentence 1 and average the embeddings for sentence 2, and then calculate the cosine similarity for these two average embeddings. Another approach is called BERT score. So what BERT score does, it actually compares all the tokens in sentence 1 to all the tokens in sentence 2, so a pairwise calculation of cosine similarity. This is a more, you could say, detail-oriented way of comparing the two sentences, and can also be done efficiently by parallelizing all these pairwise calculations on a GPU. And this is what I want to talk about next. So I'm actually going to talk about the other 4 languages first. So German, French, well, Standard German, French, Italian, and Romansh.
Oh, that's great. Thank you.
Yeah, so an encoder model that supports several languages, it's called a multilingual language model. And there has been a lot of research in the past, you could say 5 to 6 years, how to create a multilingual language model. And very interestingly, it's much simpler than you might think. So in a seminal paper by Conoe and others from 2020, they tried to perform masked language modeling on 100 languages simultaneously. And they used the simplest approach that you could think of. They just took text data like Wikipedia, articles, etc., in those 100 languages and used them as a single training set for pre-training. They didn't even tell this language model what are the different languages, or this text is in this language and this text is in another language. The model had to figure this out by itself. So the language of the training examples wasn't specified to the model. The model had to learn end to end that there are different languages and that the texts in the training data are from different distributions. And going further even, there was a single vocabulary. So the model didn't even know that, for example, the English word for has a different meaning than the French word four. All the inputs words were represented using the same word embeddings. So the model had to use the context of these words to disambiguate, does this mean English for, or does it mean oven and it's a French text? And what's really exciting is that it was found around this time that this works. So the model, if it's large enough and trained on enough data, can in fact work in all of those 100 languages, for better or worse. However, it was also found that there is this phenomenon called curse of multilinguality. So maybe if you have a machine learning background, you know the term curse of dimensionality. This is a similar idea. It's the idea that on the one hand, you need to have, so the language model needs to have a certain smallness. It needs to have a limited capacity in terms of parameters so that it is forced during training to make connections between the languages. There needs to be this pressure to actually not learn every language separately, but use the same representations to represent different languages. On the other hand, if we add more and more languages to a neural network of fixed size, then this will be to the detriment of the languages underrepresented in the data set. So they will be in a way overwhelmed or drowned out by the languages for which there are more resources. So that's the gist behind the curse of multilinguality. So what does this mean for our project? So first of all, let's look at what training data we had available for this Swiss model, which we called SwissBird. What we used was a database of online news articles or printed news articles in the 4 languages. Quite a lot of articles. So for German, we had almost 18 million articles, but the distribution is really unequal. So for Romansh, we just had 33,000 articles. So it's several orders of magnitude less. So what does this mean for this multilinguality of the model? In total, we had available for training around 12 billion tokens. And here's again a question for you, just that you can develop an intuition for tokens. So do you think that 12 billion tokens, is this a lot for training a language model, or is it actually not so much? So the original BERT model, it was trained on a quarter of that. It was trained on around 3 billion tokens. So from that perspective, it makes sense to have 4 times as many for 4 languages. And so given these training data that we had available, what does it mean for this curse of multilinguality? We had to think about how we can, in a sense, preserve the smaller languages like Romansh and make sure that the model can also learn something about those, even though there's limited data, just 33,000 articles. We also wanted to use a pre-trained encoder. So we didn't want to train a model from scratch. We wanted to reuse an existing multilingual model and perform what is called adaptation or language adaptive pre-training. We wanted to add the new language, Romansh, and learn something about like facts and figures from Switzerland, from these Swiss news articles, without forgetting what the model previously learned during pre-training. So this was the technical challenge that we had to address, and the solution was published around that time. It's called language adapters. Now, the idea of language adapters is that we have some components in the transformer that are reserved for one language. Did you cover LoRa in this class?
No. Didn't, no.
Yeah. So LoRa is also something that's quite popular when like adapting large language models. And this is a very similar idea. It's the idea that we route the computation through different modules in the transformer depending on what's the language of the sample we're currently looking at. So if we look at the text and we determine that it's German, then we have some parts of the computation in the transformer that's shared between the languages, but here we take a direction to feed forward module that's just for German. And when back-propagating the loss, we're just updating the parameters in the German module. And should be 4 adapters, right? There should be an adapter for German, 1 for French, 1 for Italian, and 1 for Romansh. And it has been shown by Pfeiffer and others that this technique of language adapters effectively mitigates this problem of the curse of multilinguality. So when we trained SwissBird, we built on this previous multilingual model called XMod that contains 81 language adapters. And we just had to think about what parts of this model do we need to adapt and which parts can we just keep. What we did was we trained 4 language adapters, 3 that were basically fine-tuned or adapted because German, French, and Italian were already part of XMod. But for Romansh, we had to create a new adapter. The rest of the transformer was kept frozen, so we didn't even update these parameters during pre-training. except for the embeddings, because we want to have our own vocabulary, and we want to have embeddings that are compatible with this vocabulary. So before I show you the results of this experiment, are there any questions when it comes to the training setup?
Yes, I have one question, please. For when creating the adapter for Romansh, was it like challenging because it's not like a really popular dialect, or like it has some scarcity of some sort?
Yeah.
Yeah, because when we try to work on something like in Egyptian Arabic dialect, sometimes it is challenging due to also lack of resources, because most models target like modern standard Arabic. So was it like in the same way?
That's a good point. So on the one hand, if there's limited data, the language adapter, so this very idea of having an adapter for a language, so this design idea has been chosen because of the data scarcity, because the language adapter will guarantee capacity inside the transformer just for this language. And the other languages cannot intrude, in a sense, into this adapter. On the other hand, it can make sense to have some information exchange between the adapters. So for Egyptian Arabic, it could make sense to maybe start with an adapter for standard modern Arabic that's already part of XMod, I assume, and then to fine-tune this adapter for the Egyptian dialect. In the case of Romansh, because it's related to Italian, we tried starting with the Italian adapter and then fine-tuning this adapter for Romansh.
Yes, okay, great, thank you.
Okay, so I'm almost done with my slides on Swiss, but I want to show you two selected results that I think are really exciting. I want to show you results for named entity recognition and for alignment. So this was previously mentioned by a student, the idea of comparing two sentences and finding similar sentences in two languages. So for named entity recognition, we wanted to be able to do something like this: look at a text and find all the person names, location names, organization names, and miscellaneous names, and color them differently. This is a standard task in NLP. I actually created 4 test sets for the 4 languages based on news articles so that I can evaluate the model in domain. And this is what I found. Maybe as expected, the SwissBot model, when fine-tuned for named entity recognition, it had a higher accuracy than baseline models because it has been pre-trained or adapted to news articles from Switzerland. On the other hand, I think it's just exciting that pre-training or adaptation works so simply. It's something about deep learning that still excites me. Interesting is maybe Romansh, because we didn't have any training data for named entity recognition in Romansh. So what we did is what is called zero-shot evaluation. So evaluation without training. We want to find out if we train SwissBot on an Italian, French, and German named entity recognition dataset, can it take this knowledge and apply it to Romansh? And interestingly, this just works. So the zero-shot performance of SwissBot is much better than the baselines, simply because this model has been pre-trained on those 33,000 articles in Romansh. Oops. Yeah, so obviously we weren't the first people to show that zero-shot transfer works, but it's still something that I find exciting to experience firsthand. Secondly, so word alignment is the idea of looking at two sentences that have the same meaning in two languages and then to like draw links between the words that mean the same thing. This is useful for corpus linguistics. It's also useful for then making a statement how similar or dissimilar are the two sentences semantically. So this is this BERT score metric. So we did that for German and Romansh. And so the accuracy of the word alignment, again, was much higher after we trained this Swissbot model on the 33,000 Romansh articles. And for the sentence retrieval task, where the goal is to, so you have 1,000 sentences and you need to find the sentence that matches the input. We achieved almost perfect accuracy. And again, it's a result that you might have expected, but it's just exciting to experience this, that pre-training and adaptation just works. So it worked for Romansh, and I'm sure it also works for other low resource languages. So I want to show you a couple more slides on Swiss German, because people asked about this in the beginning. So up to this point, we didn't train Swissbot on Swiss German, just on standard German as you find it in news articles. And Swiss German actually looks like this. So it's this is a tweet from Roger Federer, a tennis player, and in this tweet, he's using dialect in written form. Just a few years ago, this was very uncommon to write down dialect. With social media, this has changed, and now there's also this need to be able to automatically process dialect in social media posts. I don't speak Arabic, but I've heard that in Arabic there are similar phenomena, especially also this orthographic variation, that people use different writing conventions to express Arabic in social media. So this is an interesting challenge for NLP. Just to illustrate this variation that we have in Switzerland, even though there's just 5 million people that are proficient in Swiss German, but if you then take a sentence like, in the mountains, isolated showers are likely, and you ask people from Bern, how would you express this in Swiss German, and from other places, it looks wildly different. So this was one challenge, this dialectal and orthographic variation when trying to extend Swissbot to Swiss German. The other challenge that we faced was that it was difficult to find many training examples. So we just had 18 million tokens, which is again 1,000 times less than what we had for the other languages, and it's even 1 million times less than what LLMs are trained on. So in this project, we tried different approaches. So on the upper right, we have, again, the idea of just training another language adapter for Swiss German. We also tested so-called monolithic approaches. So this is like the opposite of modular, where we just train the full model on what we have. And because of this orthographic variation, we thought that maybe instead of working with subwords, it could make sense to do the training on character level. And for that, we used an approach called K9. It's similar to masked language modeling, but it's done on the character level. So this gave us these 4 combinations of architectures that we tested. So what we found when evaluating these models on Swiss German sentence retrieval is that almost all of them worked. So but maybe the most boring approach, so just training, fine-tuning XLMR on Swiss German examples on the subword level, this worked best. And what didn't work was trying to have a character level language adapter. So this was a bit a negative result, but it also shows that simple is often the most effective, even for low resource languages. So if there's no more questions, then I have 2 more slides. So first of all, I want to give you an outlook. So these experiments were done 2 years ago. Are they still relevant? I would say absolutely. I was trying to make the point that even if we have LLMs now, and obviously LLMs are useful for NLP, for every task in NLP, encoder models are also an important concept still. They are efficient, they are small, they work well for supervised training. And maybe some of you have heard about RAG, so the idea that an LLM tries to retrieve relevant documents before giving an answer, and RAG also uses encoder model to quickly find relevant texts. However, last December, Modern BERT was released. So this is like, you could say, a new version of BERT that uses a slightly different architecture, is more efficient. So if you use an encoder in your work, then I would recommend looking at Modern BERT first. And finally, you can also combine LLMs and encoders. So for example, if you want to, let's say, perform classification, then one paradigm that is now possible is to use LLMs for creating the training data, for labeling texts, for training an encoder model, and the encoder model can then efficiently perform the classification at test time. I want to acknowledge the co-authors that did this work together with me, and I am also on LinkedIn and on Blue Sky. So if you want to stay connected, then please go ahead and connect. Okay, well, thank you so much for inviting me, and it was a pleasure. Thank you.